quickly reviewing that Fermat's theorem said a raised to p minus 1 equal to 1 for all a's as long as p is a prime number. Right? As long as p is a prime number, for every a raised to p minus 1 is 1. Euler strengthened that one by saying that you really don't need to go to p minus 1, you can do it with much less, and that less is called Euler's Totient function. So for every prime, a raised to Totient function minus 1 would be equal to 1. Actually, that is the next, that's the Euler's theorem. Euler's theorem says it not minus 1. A raised to phi n equal to 1 mod n as long as n is prime. Okay. So phi n is the Totient function, and the Totient function is the residues which are relatively prime. So for example, for 10 you write down the whole number 0 through 9 and then remove the numbers that are not relatively prime. For example, 2, 4, 6, 5, okay, 2, 4, 5, 6. Those have something in common with 10. So the greatest common divisor is not 1, it's more than 1. So you remove those and then you get 1, 3, 7, 9. So that is the Totient function 4, right? So in this case, any number raised to 4 will be equal to 1. As long as you do mod 10. Okay, so for any n where GCD of a, okay, that's another condition here, that GCD of a and n has to be 1, which means that this will apply only to these 4 numbers, 1, 3, 7, 9. 1, 3, 7, 9 will give you 1 when raised to power 4. So 3 raised to 4 is 81, which is 1 mod 10, and similarly you can do the check for 7 raised to 4 and 9 raised to 4. Now similarly for 11, 2 is that, and the residue, I mean basically the Totient function is 10, and therefore 2 raised to 10, that is same thing as Fermat's theorem then, because the Totient function is actually equal to p minus 1 for all primes. Now all these rules you have to remember, because all of these are going to use in the next chapter, which is the public key. All of these are used, and that's why we are putting them together here. We use the Fermat's theorem, we use the Euler's Totient function, and then we use the Euler's theorem and whatever else is coming up in this chapter here, 2 or 3 more things. Any question about this so far? Is that if you have a prime number, then any number raised to prime minus 1 is 1. That prime minus 1 is actually what we call the Totient function, because if it is not a prime, then there is another Totient function that you can calculate by just factoring it. So the way you calculate the Totient function by factoring it is that you factor it into a prime, into primes. For example, 10 has a factors of 2 and 5, right? And then you calculate the 2 minus 1 and 5 minus 1 and multiply that, and you get 4. So the Totient function for 10 is 4. So then the members of this set of 4 are 1, 3, 7, 9, and then when they raise to 4, they give you 1. So given that, now you should be able to, given any number, you should be able to get the Totient function. If it is a prime, then it is simply p minus 1. If it is not a prime, then you factor it. For example, phi of 21. You factor it, the 2 factors are, what are the 2 prime factors for 21? 3 and 7. So you multiply them minus 1 each from each of them. So p minus 1 and p minus 1. So 3 minus 1 times 7 minus 1, you get 12. That is the totient function. So there are 12 members in this set. When you write the number from 0 to 21, you can remove everything that is not relatively prime to 21. That set will have 12 members. And for each member in that set, when raised to the power 12, you will get a 1. Is that any question about that? Is that clear? Okay. So Euler's theorem simply says that a raised to phi n equal to 1 mod n. Now n doesn't have to be prime. N could be product of primes, and if it is product of primes, you can calculate phi n, right, by subtracting 1 from each factor and then multiplying all of them, right. So you can calculate phi n, and once you know phi n, then you can calculate any a where the a is relatively prime to n. All right, there are 2 or 3 more things we need, and one of the things is to check for primality, to make sure that we can check that this number is prime. Now for a small number it's very easy, but for large numbers it's very difficult. So Miller-Rabin gave an algorithm which is stated here, and I have drawn this flow chart. This is not in the book, but I think this is basically, I drew it based upon my understanding of this algorithm. And so the idea is, if you have a large number n and you want to test it, you have to find 2 integers k and q, such that 2 raised to k times q is n minus 1, because n is, if it is even number, obviously n is not prime. So n has to be odd number. If it is odd number, you subtract 1. If you subtract 1, you get an even number. Once you get the even number, you take out all the powers of 2, and so you get then basically a number q which is given, which is clearly odd, right. So you find n minus 1 equal to 2 raised to k times q. Now you select any random number a. So this test actually doesn't test it doesn't guarantee that you got the prime number. What it guarantees is that you didn't get a prime number. If the test fails, then you know that it was not a prime number. But if it passes, it simply says inconclusive. We don't know. So there are 2 outcomes. Composite means it's not a prime number, or inconclusive. So far whatever you have tested, we don't know whether it is prime or not. So you do it many times, and if you have done it 100 times, you are kind of assured that looks like it is a prime number. Alright, so the test goes as follows. You take any number, random number a, just generate a random number. We taught you how to generate a random number, and raise to q mod n, and then calculate is it 1. If it is 1, then you stop right there, inconclusive. Take another a, go for another a. If it is not 1, then is it n minus 1? Yes, it is n minus 1, then inconclusive, stop right there. If it is not n minus 1, then you square it. Is that n minus 1? Yes, inconclusive. If it is not, then you stop. So basically you keep doing this all the way to 2 raised to q minus 1. And if that is n minus 1, then inconclusive, otherwise it is a composite. So to find the composite, you have to do lots of steps, but you might be able to get that we can't reach any conclusion with this a, and therefore we should go back and select another a. Every time you select a, the probability that it is prime is, after t-test, is 1 minus 4 raised to minus t. So every time is 1/4 decreases, right? So if you do, for example, for t equal to 10, you do 10 numbers like this, the probability is 1 minus 4 raised to minus 10. 4 raised to minus 10 is 2 raised to minus 20. So it's a very small number, right? 1 in a million chance that it is not a prime, and and rest 5 9 is prime. 6 9 is almost a prime. So this is good to be so much sure, because generally we are talking about 100-digit numbers or 200-digit numbers, big numbers, and if you were to do brute force, you would be doing it forever. So you just take any 100 random numbers and then test it out with this method. Okay? This is something that is actually, you could even write a program, and I'm not going to ask you to write the program because next Monday is the exam. So this week there won't be any homework. Next Monday is the exam, so hopefully you will read it anyway, because you will prepare for the exam, so I'm not giving any homework. But you should know this test, because when you do public key, you need prime numbers like this, large prime numbers, 100-digit prime numbers. And so you need to check them from Primality, right? So this is the algorithm. Any question about this algorithm?
So you're saying this is not going to be on the upcoming exam?
Well, here's the thing. If I were to ask on the exam, I can ask, and then what I would say is I would give you n, and then you will have to find out that you need to find k and q, and then I might give you a value of a, and then you just check it. So I'm not saying this won't be in the exam. I'm just saying that this is something that is suitable for writing a program, because many things we did, and I said, you don't need to write a program, because particularly in the secret key stuff, everything was non-linear. Everything was tables, right? And you have to make, before you can write a program, you have to make 16 tables or 20 tables or 16 tables. Here it's just the opposite. In the public key, as we are getting into public key, things are very mathematical. So interestingly enough, there are no big tables to be seen. It's just you have to be able to do multiplication and division. So you can start writing programs. All right. So one more time. I think you should probably just remember this flow chart. So if I gave you an a, then you just square it, sorry, a raised to q, and then see if it passes. Okay. All right, here's an example, 29. So for example, I could ask this one of these two examples. It's one, actually I don't have to ask these two examples. I could make up an example like this, another one. So 29, you want to see whether 29 is prime number. Right? So 29 minus 1 is 28, which is 2 raised to 2 times 7. So k is 2 and q is 7. So we take any number between 1 and 29, or 0 and 29. Obviously 1 would not be a very good number, but let's say we took 10. We raised 10 raised to 7, mark 29, and that's a lot of mathematics. Once you did that, it comes out 17. So it's neither n minus 1 nor 1. If it was 1, it would be inconclusive, and n minus 1, it would be inconclusive. So 28 would be inconclusive, and 1 would be inconclusive. Right? That is the first part of the diagram here. A raised to q mod n is 1. A raised to q mod n equal to n minus 1. It's not. So we go to the next one. Third branch. We square this number 17. Why 17 we square it? Because we want to now square this number by 2, and this is same thing as squaring that number. So to go to 10 raised to 14, all we have to do is do 17 square, right? And we do mod, and it comes out 28. So we finish the test in the third branch. 221, we do the same thing. 221 minus 1 is 220, which is 2 raised to 2 times 55. All right. So the main thing is this q is what we have to raise every time. So if the q is large, you have to raise to a large power. So let's say we randomly took a equal to 5 raised to 55 mod 221, that is 112. And 112 is not neither 1 nor n minus 1, so that doesn't do. But we do a square of this, and that is neither 1 nor n. Actually, this is not n minus 1 either. So that finishes the test, because the test ends when you have done up to 2 raised to k minus 1. Sorry, this letter here is k. Okay. So in this example that we were doing, k was equal to 2, and therefore 2 minus 1 is 2. So as long as you did this square, you are at the end of the table. Right? In both these examples, k is equal to 2, and therefore all you have to do is square it, and at that point you would get one of the two results, either inconclusive or composite. Does that answer? Can you do this kind of thing? Actually, basically, given a number, I won't give you a big number, but a small number, you should be able to just find k and q and then do the test until it gives you one of the two results. Okay. Any question about this test? If not, then we move on to the prime distribution. Is that how many primes can you find in a given range? So here are the prime numbers 1, 2, 3, 5, 7, 9, 11, 13, and so on and so forth. As the numbers become bigger and bigger, the prime becomes rarer and rarer and rarer. Right? In the beginning, there are lots of primes. Oh, sorry, 9 is not a prime. Okay. So this is the key thing, is that the number of primes is close to, the distance between the primes is close to log n, natural log of n. Everybody knows what is the natural log, right? Base e. So this is natural log, but yeah, basically, right? So in practice, you need to do 0.5 times log n numbers of size n to locate a prime. So if you need a prime of 100 digits or so, take natural log of 100 digits, that is 200, it will come out more like 200 or 300 times 0.5, 150 numbers you will have to try out before you will get a prime. Obviously, you won't be trying any even numbers, but you will need 150 odd numbers, and you will go through this test which we talked about a minute ago before you will find a prime. And that doesn't really guarantee, this is 0.5 log n, doesn't guarantee that you will find a prime. It's quite possible that all those 150 turn out to be composite. So that's. Now, one very important theorem which is coming up is Chinese remainder theorem, and this one you have to practice a lot. If it was not the exam, I would have given you 1 or 2 problems for sure to do as the homework, and maybe there is a homework here. Yeah, there is a homework which will not be due. But Chinese remainder theorem is another thing that we use in public key, and all it does is that if you have a large number, you want to do a mod of a large number, if the large number can be factored, then you can do small mods. So if big M is equal to M1, M2, Mk, then you can do mods M1, mod M2, mod Mk, and then somehow combine them to get mod M. Okay, so you can use little moduli, and so the formula is a little bit complicated, but once you do it 2 or 3 times, it becomes very trivial to understand. But right now the formula is written here: A mod M, where M is large number, is equal to, you go with each moduli separately, and or each modulus actually, I don't know, moduli anyway. So A mod Mi, little mi, times the inverse, basically M upon Mi, so this means the rest of the M's, because M is a product of M1, M2 to Mk. When you put Mi in the bottom, this leaves everything else, times M upon Mi, the same number inverse mod Mi. Now this is fixed number, this doesn't depend upon A, and therefore you can calculate this beforehand, this whole thing beforehand, even this one beforehand. So you can calculate this beforehand, and every time the number A changes, all you do is A mod Mi, which means M1, and then A mod M2, A mod M3, A mod Mk, and then for each of those numbers you multiply by this pre-calculated quantity. Okay, so let's try to do this. We want to find out what is 452 mod 105. Now obviously we won't be doing it for this, because by the time we do all this Chinese remainder theorem, we can calculate 452 mod 105. But just imagine that 105 was a big number. Okay, and then this one comes handy, and obviously for that 452 has to be a big number too. In fact, if the modulus or moduli is 100 digit, then for anything less than 100 digit you don't need to do anything. It's only when you have 200 digits, then you need to divide and find out what the value is, right? So these are big numbers, imagine. So anyway, 105 has 3 factors: 3 times 5 times 7, right? So we can calculate 452 mod 3, we can calculate 452 mod 5, we can calculate 452 mod 7. To each of these 3 mods, we multiply these 2 quantities. First quantity is this big M divided by 3, big M divided by 5, and then big M divided by 7, and then the second quantity is the inverse of that mod 3, inverse of that mod 5, inverse of that mod 7, and then we add up all of these. Alright, so first let's see, how do we find out this quantity? 1 upon 05 divided by 3 is how much? 35. So we want to find out 35 inverse mod 3. 35 inverse mod 3. So let's say 35 inverse is equal to mod 3 is x. That means 35 inverse is x mod 3, or if you were to take other way around, 35x is 1 mod 3. So what value of x will give you 1 mod 3? If you put x equal to 1, 35 mod 3 will give you how much? 35 mod 3 is how much? 2. So that is not 1, right? If you put x equal to 2, how much is x? Then it will be 70. 70 mod 3 is 1. So x equal to 2 is the answer, right? But there is a better way to find this x. Does anybody remember how you find inverse? Nobody remembers how you find an inverse? There was a tabular method we had talked about of something. Did you guys do a tabular method for the homework?
Yeah.
And you forgot? Okay. All right. So the real method to find the inverse is by the tabular method. You would write down, when you want to find out 35 inverse mod 3, you would write down a table with 3 and 35 and do the whole table. It should not take many rows, but within 1 or 2 rows you will come to 2, and that you will know that the inverse is 2. Similarly, you need to find out the second here. This one is how much? 21 inverse mod 5. 21 inverse mod 5. And you will need to do that table here and then find out that in that case the inverse is 1. And here we need to find out 15 inverse mod 7. And that will tell you that x is equal to 1. So, we found the inverse, we put the values of those inverses and then we multiply. So, this one is 2 times 35 times 2. This one is 2 times 21 times 1. This is 4 times 15 times 1. You multiply the whole thing, 140 plus 42 plus 60 mod 105, 242 mod 105 is 32. Alright, so really, I mean, we did so much calculation, we could have for 105, we could have just divided that and gotten 32. However, if 105 was a big number, again I should say that this one comes very handy. For small numbers, it doesn't really help that much. And I am going to repeat this so that everybody understands. I know there is a lot of mathematics here, but the formula is, so Chinese remainder theorem helps when you have a modulus which is a product of many moduli. Moduli is the plural of modulus. Okay. So you can do piece by piece. You can do mod respect to each, and then you can multiply with something that you have pre-calculated. So these things are pre-calculated, they don't depend upon A. And the way you pre-calculate is that you divide m by mi and then you multiply by its inverse. So this is interesting. We take whatever number it is, 35 times 35 inverse. Right? To find the inverse, you need to use that table method, or you can just do by inspection method. This is what we call inspection method here, is that we want to find out what is the value of x that will give us mod 3, and so basically same way we can write down, we can bring x on the other side, x and 35. So basically we bring 35 on this side, so we get 35x equal to 1. So x equal to 1 we try out and it doesn't work, x equal to 2 works and we get x equal to 2. So this is inspection method. For small moduli it works, right? But for large it will not. I mean, for large you really need to do the table, because you will otherwise be trying out every possible value of x. Does it look like something you can do? Now this will be in the exam for sure. I don't have any exam in which I did not ask about the Chinese remainder theorem. So you are guaranteed. There will be a problem in the exam where you will be given the numbers and you have to do Chinese remainder theorem. Because this tests everything that we need to test, many things actually, not everything. It tests that you can do the tabular part, that tabular thing, then I don't want to give you a separate problem for table. And then it tests that you understood all of this, much of it. So please ask any questions if you have any question right now. And George is absent today, right? Yeah. Any questions? Everybody feels this they understand that? Or is it totally over the head? I kind of don't get the feeling as to whether it is. You do have to do 1 or 2 problems yourself, then you get it. And so basically I think the same thing that was said here, I have said it here again, so I am not going to repeat that. Here is an interesting problem. For a parade, marchers are arranged in the column of 7, but one person is left out. If we arrange them in column of 8, 2 people are left out. If we arrange them in column of 9, 3 people are left out. So how many marchers are there? So this is actually application for the Chinese remainder theorem, because we know x, whatever x is equal to 1 mod 7, it is also 2 mod 8, and it is also 3 mod 9. We don't know x. So in the previous example, we had given you x and you did the mod. Here we don't know x, but we give you the modular values. So the question is, what is x? Okay, so it's the same formula as here, but you need to find out a. You are given a mod mi, you are given all of this, you can calculate. If you do all of this, you can get a. Right? So let's see. So n in this case is 7 times 8 times 9 is 504, and we are given 1 times 504 divided by 7, and then the inverse of that with mod 7. Then 2 times 504 by 8 with inverse of that mod 8. So this inverse is with respect to mod 8, and similarly this one inverse mod 9. So now you have to calculate what is the inverse of 72 mod 7, what is the inverse of 63 mod 8, and what is the inverse of 56 mod 9. If you calculate that, somehow you will know that that is 4, 7 and 5. Those inverses are 4, 7 and 5. Once you know that, you can multiply them together. You will get a number like 2010 mod 504. You subtract it, you get 488. So there are 488 marchers. Now you can verify that that is correct. 488 mod 7, you should get a 1. I mean, basically you divide 488 by 7 and then see whether you get a 1. I don't get a 1. Let's see. 488 mod 7. 42, 68. I get a 5. 68, 68, and then 63, you get a 5. So that number, that answer is incorrect, but whatever is the correct answer, if you would have gotten the correct answer, then you would have gotten 1, 2 and 3. Double check. Alright, now I can later on check it out as to where it is wrong. Maybe that's something that you can do it yourself too. So this answer is 488, doesn't look like. Now let's just try 488 mod 8. 488 mod 8 is 0. So this answer is clearly wrong. Alright, so now let us see. Let's add up these numbers. 288 plus 8882 is 1000. 170. 170 and 840 is 170 is 9, 10, 10, 10. Yeah, 2010. So this part looks like correct to me. Now when we subtract 504, 504. Yeah, so this looks like it must be 498. 504 times 4 is 2020. So 10, 2020. 2020 minus 29. So it's 10 less than 404. 494. Let me try 498 or 494. Anybody has a correct answer?
It's 498.
498. This is a latex. I can't correct it right now, but you can write down 498 and then let's check it out with 498. 498 would give you 1 mod 7, that's for sure. 49 and 8, that's correct. 498, when you use 498, you get 2, yeah, 2 mod 8 is correct. And 498 divided by 9, 45 gives me 48, 3, yeah. So 498 is the correct answer, and you can double check that. Okay. All right. So primitive roots. So what is a primitive root? A primitive root is one which has which is co-prime, and basically if it is co-prime, then it will satisfy this condition: a raised to phi n is equal to mod n equal to 1. And then if P is prime, and now here's the thing, though, sometimes in this whole chapter they are mixing up P and N, and so there is a problem. Let's just put N. So if N is prime, then it will generate the group mod N. All right, because if N is prime, then phi n is equal to n minus 1, right? And therefore you will generate the whole group. So here is the thing: n, let's say mod 19. Mod 19, if a is 1, all the powers of 1 are given here. If a is 2, all the powers of 2 are given here. If a is 3, all the powers of 3 are given here, and so on and so forth. Notice that everything raised to 18 is 1, right? But you don't have to go all the way there. For some things you can do it much less. So for example, you get for 1 you get a power 1, but for 4 you get power of 9, for 5 9, and this one, and for 7 you get 2, and so on and so forth. So these are the primitive roots. Oh, sorry, primitive roots are the one, I'm sorry. Primitive roots are the one that don't get a 1 before they reach the end. Because with 2, you have to go all the way to 18 to get a 1. And therefore it will generate the whole set, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, up to 19 in this set. And similarly with 3, similarly with 10, similarly with 13, 14, and 15. These are the primitive roots. The primitive roots are the one that require the complete p minus 1 to make them 1. Other values that don't require full, they are not primitive roots. So they can generate the whole set. They are also called the generator for this whole set. Either one of them will act. Any one of them will act as a generator. 2, 3, 10, 13, 14, and 15. Obviously, this is a good exercise for Excel. You can write this in Excel and give any number and it will prepare the whole table, and then you can see which are the primitive roots. All right. Okay. Now that we talked about the primitive roots, the last thing that we need to talk about is the logs. So what is the definition of the log? And here we are talking about discrete log, not the real, not the other ones. So if b is equal to a raised to I mod p, then I is the log of b base a mod p. So it could be written either as a discrete log discrete log base a of b mod p, or sometimes we write log 3 comma, we also write the p right there in the along with that, so we know what the modulus is. So for example, if somebody asks you what is the log of 4 base 3 in mod 13 arithmetic, what is the log of 4? What power of 4 will be equal to 3. No, sorry, see, log, so sorry, what power of 3 will give you 4? No power of 3 will give you 4. Right? So the discrete log doesn't exist. But if somebody asks you what power of 2 will give you 3, that has the answer 4. Because 2 raised to 4 is 16, which is 3 when you do mod 13. So now you know how to take log in mod, right? We did how to multiply, how to divide, and so on and so forth. Now we know how to do log. But one thing to notice is that the log is even harder than exponentiation. Exponentiation is difficult. You have to multiply so many times. But log is very difficult. So this is what this is the basis of this whole public key. All right. So for 19, if you take log base 2, then for each number, this is the answer. How did we get this answer? We can go back to the previous table, and if we are doing base power of 2, then we know that the log of 4 is 1, log of 4 is 2, log of 8 is 3, and log of 16 is 4, log of 13 is 5, and so on and so forth. So you read the number here, and the power here gives you the log, right? So you can write down this in another method here, where here is the number and here is the log. So when you raise 2 raised to 18, you get a 1, 2 raised to 1, you get a 2, 2 raised to 13, you get a 3, and so on and so forth. We are mod 19. Similarly, then you can do base 3, base 10, base 15, base 14, and so on and so forth, because these are all primitive roots. If it was not a primitive root, then what will happen? Suppose you select 7. 7 is not a primitive root. Then you won't be able to get log of anything other than 1 and 11. If you want to get a log of 8, there is nothing there, because no power of 7 is equal to 8. No power of 7 is equal to 6. No power of 7 equal to 9. So the discrete log base 7 does not exist. Okay, but discrete log base 10 exists for all numbers. Discrete log base 9 doesn't exist for all numbers. Only these many numbers can be generated with 9. And similarly with 8 doesn't exist, and so on and so forth. So only primitive roots will give you all the numbers, and the logs will exist. And for our class, the best way to find primitive root is by exhaustive enumeration. So if I ask you a question whether 2 is a primitive root of 19, you just have to write down 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, and so on and so forth. All right? All right, that finishes this chapter. And let's revise, let's just slowly go through each of the points we said. First of all, Fermat's little theorem said that a raised to, for any p where p is prime, p minus 1, a raised to p minus 1 is always 1. For any prime number. If it is not a prime, then we need to find the Euler's Totient function, and then a raised to Euler's Totient function is equal to 1. And what is the Euler's Totient function for a prime p? What is the value of the Totient function for p for prime numbers? For prime numbers it is equal to p minus 1. For non-prime numbers we just find out all the primes and multiply their minus 1, p minus 1, p minus 1, you know, whatever numbers those are, right? So that is you have to remember, right? Then primality testing, you do the testing, and that was the Miller-Rabin's test, was that you first express it as 2 raised to k minus q, then you take any random a, raise it to the power q, and see if it is 1 or n minus 1. If it is not, then you go to square and cube and so on and so forth, and Actually, I missed here one more point, that should be a raised to q equal to n minus 1 or 2q equal to n minus 1 and so on and so forth, and then you know whether it is composite or inconclusive. Then the Chinese remainder theorem, we studied Chinese remainder theorem. All it does is that you divide the big M into little m's, and then you can calculate the complete mod by piece by piece, by inverting things. Right? Then we talk about the primitive roots, and the primitive root is the one that generates the whole set. If it generates the whole set, then the lowest value of m that will give you a raised to m equal to 1 is equal to p minus 1, and therefore you can take a log with respect to that. And if it is not a primitive, then many of the logs will not exist, and the log is defined as usual. Okay, so sometimes we write like this, either d log or just log b comma p, where b is the base and p is the modulus. Now this homework 8 is not due, but you should do it. Alright? So first you have to use the Fermat theorem to find a number x between 0 and 22 such that x raised to 111 is congruent to 8 modulo 23. Alright? X raised to 11 is congruent to 8 modulo 23. So now, whenever you have to do problems like this, first of all you should notice that all of the numbers can be reduced below 23. So this 111, first thing is that you should reduce that to below 23. Right? Once you reduce that power to below 23, because everything raised to 22 would be equal to 1, so you just 110 can be taken out right there. Right? So do not use brute force searching. Right? Then Miller-Rabin test to test 19 for primality. Now here I would have said more likely, here in the home you can probably do all the numbers between 1 and 18 and whatnot, but or whatever makes sense. But here I would have said, try two numbers, two random numbers, or I would have given you two numbers that you have to try. And then x equal to 2 mod 3 and 3 mod 5 and 5 mod 7, what is x? What theorem you have to use? Chinese remainder theorem to find that, right? So you will do 3 times 5 times 7, 3 times 5, 7, 105, and then you do, just do the inverse and all that. Primitive roots of 11, this one is exhaustive search. Basically, you want to find out all the primitive roots of 11, just see, where if you find a number that takes less than 10, then you cross that out, and if it goes all the way to 10, then that is a primitive root. Find the discrete log of 17 base 2 mod 29. Again, you have to just write down all the powers of 2. Actually, you don't have to write down all the powers of 2. You just have to write down the powers of 2 until you get 17.